exponential function, f of x is equal to x in exponent x. If we are drawing this function, or if we are plugging in this function in the Desmos or other graphing calculator, the graph is going to be as it looks here in the picture. And the domain of the graph is going to be from a 0, so it includes 0, to infinity. And the range of the function is going to be, or is, to better say, from 0.692 to infinity. And why doesn't have a here graph in this from minus infinity to 0? It doesn't have it because if we have a function, exponential function, when the base, let's say, is a negative function and exponent is a negative function, then we're going to have lots of the complex numbers of the complex number, and whenever we have those complex numbers, they are going to show in the graph as an interception, or the function is going to be discontinuous in all the points where the values are going to get the complex numbers. And those complex numbers are not going to show in the real plan. That's why we don't have here the graph from minus infinity to 0, but the only graph that we have continuous is from 0 to infinity. Now let's see and let's justify this point here, the point of intersection, 0 and 1. X-intercepts. X-intercepts, for example, if we're looking for x-intercept, let me take this red. We are looking at y is equal to 0. We set the y is equal to 0. If y is equal to 0, we're going to have the function 0 is equal to the x in exponent x. And if we are converting this into the log, we're going to have a log of a base x of a 0 is equal to x. And if we are subtracting both sides with the x is going to be log of the base x of 0, log base x of 0 minus x is equal to the x minus x. And consider the x is a finite number, and log base x of a 0 is undefined. Let me write undefined just UND minus x is equal to 0. So for any value of a finite here, and undefined minus any value of a finite number is going to be undefined. Undefined is equal to 0. So as we see here in this equation, the right side of the equation is not equal to the left side. Therefore, this has no solution. So it has no solution. Thus, the x-intercept does not exist. X-intercept does not exist. Intercept does not exist. So let me write it with abbreviation, D and E. So the x-intercept does not exist. And if we are going here in the picture, we see the graph of the function x in exponent x doesn't intercept the x-axis. Now let's go to the y-intercept. The y-intercept here, let's say y, x is equal with 0. We set x is equal to 0. and y is equal with x in x. Okay, just let me take a blue. If we are taking a y x is equal with x and we plug in 0 in exponent with 0, this form is indeterminate. And according to elementary calculus, it doesn't exist by intercept. But if we are going, for example, and we take in consideration the higher calculus, then we are looking, for example, this is x is f of x and g is the g of x. And whenever, for example, f of x is going to one value and the function g of x goes to another value. Or in other words, whenever x goes, for example, to 0, we are looking what goes f of x, or this function y here, in this case what we have. And we are looking, and we're going to lnize both sides. If we lnize both sides, we have ln y is equal with x ln x, x ln x in x. And now if we take in consideration the limit here with a limit, so ln y is going to be equal with the limit x goes to 0, x goes to 0, and here is a ln. But if I have a ln x in x, according to the log rules, x is going in the front of the ln, and we have a x times ln x. So this form is a little bit easy. And everything is going to be limit. If we wanted to reorder a little bit, is going to be limit of x goes to 0, and this ln x stays here as a numerator, ln of x, and 1 over x, this x I can write in the form of 1 over x as a denominator. And now this form, if I'm plugging here, ln 0 is undefined and 1 over 0 is undefined over undefined. So we are using here the L'Hopital rules. Let me write it with a different color. We apply the L'Hopital rules. And by applying the L'Hopital rules, we can take a derivative of the numerator and denominator. And ln y is equal with the limit x goes to the 0, x goes to 0, and if we take in ln x is 1 over x, and if we take in the limit of if we take in the derivative of 1 over x is minus 1 over x squared. And now here we multiply everything by x squared. We multiply here by x squared, and we multiply here by x squared. And what we're gonna have, this is going to be ln y will be equal with the limit x goes to 0, limit x goes to 0, and here x squared with x squared simplifies. X squared divided by x is just x. And because it's just x, it can be negative x, it doesn't matter. Negative x. But if we are plugging in 0, then it implies, so ln y, let me write here down, ln y is equal to 0. if we lnize both sides, and E in ln y is going to be equal with E in a 0. E in a 0. So here is going to be y ln E in ln is equal with 1. But already we know this ln is 1. This here is equal with 1. So y is equal with 1. Y is equal with 1. And we have an intercept here in the y-intercept. When x is a 0, y is 1. So those are the y-intercept. And if you look here, so we already justified this y-intercept in y-axis. And now, if you're looking for the asymptote, does the function has asymptote? So to find out does it has an asymptote, we find the y, the asymptote is equal with the limit. We take in the limit x goes to infinity of the function x in exponent x. But as we already did a whole work here when it was a 0, we to not show whole of the process again, to not repeat, we can take just the last equation here what we have. We take just this last equation, and we can write this way: ln y is equal with let me see here again. Let me E in exponent 0. Ln y is equal with the limit. Let me write little. Let me go from this, and x goes to infinity. I will take one step further, and here it was x. We already had this equation, but it was a 0. And now from this we can find out. So ln y is equal with the infinity. Instead of the x at this limit, we are writing infinity. And when we lnize everything, and we have a E ln y. I wanted to go from this point, but I went a little bit further. So I don't think it's any big problem. And we have a E infinity. Because we have a lot of room here, so we can play around. And in the end, y is equal, E in infinity is infinity. So the horizontal asymptote does not exist. The horizontal asymptote does not exist. So usually the exponential function, they have a horizontal asymptote, but in this case we don't have a horizontal asymptote. And what does it mean? We don't have always a horizontal, the exponential function, they do not have always a horizontal asymptote, does not exist. I'm sorry, let me write this better, does not exist. So the horizontal x asymptote does not exist. So usually the exponential function, they have asymptote, horizontal asymptote, but in this case they don't have. And vertical asymptote exponential function they don't have, except when they are, for example, in combination with other functions. In those cases we may have some vertical or horizontal asymptote. But what is the most important here, when in this function here we do not have a horizontal or vertical asymptote, we have just the graph in the way how it is how it's drawn in this figure, and the end behavior of the function as x goes to infinity, f of x goes to positive infinity.